So guys, let's get back with the second problem discussion. So in the second problem, of course, if you see, this is a question based on the waves and oscillation part, right? So this is the question corresponding to the waves and oscillation part of the essay paper of 2019, right? So they have given the essay problem of waves and oscillation related with the stationary waves in a string, in a stretched string, right? So what they're saying in the first question is draw the standing wave patterns of the fundamental mode first two overtones produced by a vibrating stretched string in three separate diagrams. Mark the nodes as capital N and antinodes as A. So this is a simple question, guys, right? So if you see, so the second question, there is a stretched string, right? If you see, there's going to be a stretched string, and you know, in a stretched string, the requirement is somehow at the two ends of the string there should be a node, right? So what is the simplest waveform that you can draw such that two nodes are obtained at the two ends? The simplest waveform that you can draw is this, right? This is the simplest wave, right? So this is the fundamental mode, right? So here the point corresponding to the maximum amplitude is the antinode A. All right, okay, so that is done. So let us next draw the first overtone. All right, so somehow here also you have to have a node, here a node, right? And then thereafter the next simplest waveform that you can draw is this, right? The next simplest waveform that you can draw is this. All right, so if you see there is a node here, a displacement node, and an antinode here, the maximum displacement. At this point also an antinode, they vibrate with a maximum amplitude, right? So let us, this is the sorry so simply the fundament, this is simply the not the fundamental, right? So the first overtone, right, is going to be the first overtone. All right, okay, let us go for the second overtone. All right, the second overtone, this is going to be the second overtone. So if you see, the waveform is going to be, the next simplest waveform that you can get is this. All right, this is it. Somehow here it should be a node, 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 node. At this point antinode, antinode, and here antinode, right? So now we have drawn the waves patterns of the required things that they have asked. Okay, let us see what the next problem is. In the second part, what they are saying is obtain an expression for the frequency Fn where nth harmonic in terms of n, t, l, m, where t is the tension, l is the length, m is the mass per unit length. We need to get an expression for the nth harmonic. Expression means the frequency. So if you see, this is actually the first harmonic, right? First harmonic. This is the second harmonic, right? And this is the third harmonic. So now guys, one you need to observe this well, that is, this is, in this first harmonic there is one loop. In the second harmonic there is two loop. In the third harmonic there is three loops, right? So what is the wavelength of one loop? Lambda over 2. What is the wavelength of two loops? This is lambda over 2, lambda over 2. So this is lambda over 2, lambda over 2, lambda over 2. So the nth harmonic will have how many loops? N loops. Therefore, if we consider the total length of the string as L, it will be equal to n times lambda over 2. So like if we consider the third harmonic, it's going to have the total length will be equal to 3 times lambda over 2. So nth harmonic will contain n loops, which means n times lambda over 2. So therefore, now we have lambda is equal to 2L over n, right? So from V is equal to F lambda, what is V? V, velocity of a stretched length, a stretched string. So Fn is equal to V over lambda. You need to know that V can be written as root T over M into 1 over lambda. So Fn is equal to, instead of lambda you can write this term, that is 2L n root T over M. So this will be the frequency for the nth harmonic in terms of tension, mass per unit length, and the nth harmonic, right? Okay, cool. Let us move on to the next problem, that is the third one. In the third one, what they are saying is, for a given string, state 2 possible ways of changing the harmonic frequency. State 2 possible ways. How can we change the harmonic frequency, right? So for a given string, for a given string, if we say for a given string, mass per unit length is constant, right? It is constant, so you can't vary it, but you can vary the tension of a given string. Therefore, what do they ask? Simply, how can you vary, right? Change the harmonic. Change means one method is by changing the tension of the string. The other method is by changing the length of the string. We change the length of the string, still the fundamental the harmonic frequency would change by changing the length of the string, right? So these are the two possible ways. So let us discuss the B part. So here they are saying a harp-like musical instrument shown in figure 1, so this is it, consists of 7 identical strings, right? And then the longer string L1 produces the musical note C and the fundamental frequency 260. So like this longer string corresponding to the musical note C produces the fundamental frequency of 260 Hertz. The corresponding length of the string which produce all musical notes are given. What you need to do is, if all the strings are under the same tension, okay, all under the same tension, calculate the fundamental frequency of capital F and capital B. So for capital F, 1 over L1 is 0.7. For capital B, it's 0.53. Right, okay, cool. It's the B part, first question. So we know that F is equal to, we already got an equation, Fn is equal to n over 2L root T over M. Since we need the fundamental, right? Since we need the fundamental, since we are dealing with the fundamental frequency, n is equal to 1. Fundamental means the first harmonic, n is equal to 1, right? So therefore, F is equal to 1 over 2L root T over M. So you need to understand that each of these terms, the tension and the mass per unit length is the same, because they have already told that the tension is the same and they are using identical strings, which means mass per unit length is also going to be the same. So therefore you can come to a conclusion that the frequency of the string is inversely proportional to its length, right? So they have they have given L over L1, like for LF over L1 they have given is 0.7. For LF over L1 given as 0.7, which means LF is 0.7 L1. So for LB over L1 they have given it as what? They have given it as exactly 0.53. For C it's 1.53. So LB is 0.53 times L1. So C they have given it as LC over L1 is 1, which means LC is equal to L1. Right. So now also they have given the frequency of the node C, that is 260 Hertz, inversely proportional to LC. So if I'm gonna take it as FC inversely proportional to LC, with the first equation, with the second equation, I'm gonna divide the second equation by the first equation. FC over 260 is going to be this is right f right, so this is ff LF divided by LC, right? LC is L1, LF is 0.7 L1. This to this cancels. FC is 260 divided by 0.7. It's going to be something closer to 371.43 Hertz. Similarly, we can find for B as well, right? FB is inversely proportional to LB, third one. So here also I'm going to divide the third equation from the first equation. FB over 260 LB LC, right? LC is L1, LB is 0.53 L1. So FB is 260 times this to this cancels 0.53. So it's going to be something around 490.57 Hertz. Right? This is going to be the two answers, right? This and this. Okay. So next we need to discuss the second, right? The second one. So what it says is, to obtain a correct musical note, the frequency can be fine-tuned by adjusting the tension of the string. By adjusting the tension of the string, by what percentage should the tension of the string be adjusted to change this frequency by 1%? So what is the relationship between the tension and this is the B second part. What is the relationship between the frequency and the tension? It's F is directly proportional to root T. If you see this, F is directly proportional to root T, right? So like, let's assume when the frequency is F, the tension is T, right? So if we need to change the frequency by 1%, now let's assume F new is, if we need to change it by 1%, it's 101 over 1 times the old frequency. Then only we can say like we have changed the new frequency is 1. Like if we are changing the frequency from F to a new frequency, if the change is 1%, then it should be 101 over 100 into the old frequency, right? Then only this minus this, then only the change of frequency will be 1, like see 100 F over 100 minus F, right? So then only you will get 1% change, right? So yeah, okay, the new frequency is this. Let's assume when the new frequency is this, the tension that we need is T new. right? For f nu, let's assume the tension, like let's assume to obtain this much of a change in frequency, the new tension should be this, it seems. When the new frequency is this, let's assume the new tension is this. This is the first equation, this is the second equation, right? You just have to divide the second equation from the first equation. You will get T nu over T is equal to 101 F over 100 into 1 over F. This to this cancels. So if you square both sides, you are going to get T nu is equal to 1.02 old tension. So the change in tension to the old tension, that is T nu minus T over T, is 1.02 T. T nu is what? 1.02 T minus T over T. This is what? Simply, if you take it as a percentage, and then if you take it as a percentage, it's going to be 2%. 2%, right? So you need to understand that. First of all, what I did was, if the frequency is F, I thought, okay, the tension is capital T. Then for the frequency to increase by, after the frequency increased by 1%, I thought, okay, the new frequency is F nu. When the new frequency is F nu, I assumed the tension is T nu. So what is the new frequency? 101 times F, at 1% increased this. So I divided this and this, and I found an expression for the new tension. What I need is how much should be, by what percentage should we increase the tension. T nu is this. The change in temperature is T nu minus T over T into 100%. There is the percentage. So yeah, I got the answer to be as 2%. So guys, next we need to discuss about the C part, right? So here, actually, what it says is, a student designs and builds a set of pan pipes to produce musical notes given in the above table. By using narrow PVC pipes, right? Okay, and with different lengths as shown in the figure. Lower end of all pipes are closed with corks. So this is one end closed tube, right? What they are simply gonna discuss is regarding one end closed tubes, right? Waves in one end closed tubes. So they have asked us to draw the standing wave patterns of the fundamental mode and the first two overtones produced by one end closed pipe, right? They have asked us to draw the fundamental mode, right? The fundamental mode and the first two overtones produced by one end closed pipe of length capital L, right? Mark the nodes as N and A, right? Okay, let us do that, right? So this is the C part. So let us assume this is the one end closed tube, right? So if this is the one end closed tube, somehow at the closed end there should be a node, and at the open end there should be a antinode. So what is the stationary waveform that can be drawn, the simplest waveform that can be drawn such that antinode exists in the open end and a node exists in the closed end? It's this kind of a wave, right? Yes. So this is the fundamental wave, right? Fundamental mode. Okay, all right. So let's next consider the first overtone. They have asked us to draw the first overtone as well, isn't it? So the next possible wavefront that is possible to be drawn is this, right? It's this, right? So here, guys, if you see, here it's a antinode, here it's a node, here antinode, and here node. This is the first overtone, isn't it? This is the first overtone, right? And then what? And then next, the next possible wave is the second overtone, right? Yeah, this, right? There's going to be two full loops. There's going to be two full loops, isn't it? So this is going to be antinode, node, antinode, node, antinode, and node. So this is going to be the second overtone, right? Second overtone. And then also they have asked us to find a frequency for this, right? They've asked us to find no, simply you have to draw the diagram, right? So yes, so these are going to be the diagram. All right, guys, so let's go for the next second part. The first part is done. Calculate the required lengths of the pipes in centimeters which produce musical notes C and B. We need to calculate the required lengths of the pipes in centimeters which produces the fundamental notes C, B, right? So they have asked us to assume the velocity of sound in air is 340. So what is the frequency for a fundamental wave? Fundamental wave, this is the fundamental waveform, right? So here, guys, if you assume this is the length of the tube, right? So this is going to be, this is going to be lambda over 4. So this is half of a loop. Actually, one complete loop is lambda over 2. So half of a loop is lambda over 4. So therefore, we know L is going to be equal to lambda over 4, which means lambda is equal to 4L. So according to V equals F lambda, right? So we can write the fundamental waveform is, fundamental frequency is V over lambda. So instead of lambda, we can write 4L. So V here is, now let us find the this thing for the note C note. So for C note, let's assume the fundamental frequency is Fc. What is the velocity? Velocity is 340. 4, let us assume the length of the tube required is Lc. We know the fundamental frequency of the C note, that is 260 newtons. That was given in the previous part. It was 260 hertz. 340 4 L note. So if you simplify L note, it's going to be something around 32.7 centimeters. So similarly, we are going to find for the B note as well, right? We already know the fundamental frequency of the B note. We found it, 490.6 hertz. So we will use the equation FB is equal to V over 4LB, right? So LB is what we require, V over 4FB, right? Velocity of sound in air doesn't change. It's always constant. 4 into what is the fundamental frequency of the note B? 490.6. So if we simplify this, we are going to get LB, the length of the tube B, that should be something around 17.3 centimeters. So this is the length of the one end closed tube for it to vibrate to a frequency of 490. This is it, and this is the length such that the tube to vibrate to a frequency of 260. All right, okay, so let's go for the next part. The next part, what they are saying is the longest pipe is found to be producing a frequency of 255 hertz. Okay, the longest pipe is found to be producing a 255 hertz instead of 260. It's producing 255 instead of 260. By what distance should the cork be moved? So this part, what distance should the cork be moved to obtain the frequency of 260? Now, actually, it's like this. This is the third part, right? So guys, there is a one end closed tube, right? So this, of course, instead of producing the longest tube, actually should produce the note C, isn't it? That was what was mentioned in the previous part as well. So that is, it should vibrate to a frequency of 260, right? But actually it doesn't vibrate in that length. Instead, if let's assume the length is L, right? In that case, what it's vibrating is for 255 hertz instead of this. So we need to increase the frequency. Somehow we need to increase the frequency. So according to F is equal to 1 over L, if we need to increase the frequency from 255 to 260, if we need to increase the frequency, then actually you need to decrease the length of the tube. So therefore, I think you will have to simply decrease the length of the tube. You'll have to decrease the length of the tube, maybe somewhere here. You'll have to shift the cork up. All right, you'll have to shift the cork up, let's assume by x distance. Now what is the length? Now the current length is L minus x, right? So let's assume at this moment, of course, after shifting it by x distance, like when the length is decreased, frequency should increase. Let's assume it is increased to 260 hertz. We need to find by what amount should we decrease the length. So it's pretty simple. So for both these instances, I'm gonna write what? F is inversely proportional to 1 over L. So for the first instance, the frequency was 255, the length was 1 over L. For the second instance, frequency was 260, length was, what was the length? L minus x. Length of the tube was L minus x. So I'm going to divide these two equations, right? I'm going to divide 2 by 1. 255 over 260 is equal to L over L minus x. So can you do that? If you do that, of course, you are going to get an L, right? Do we know L? Not exactly, isn't it? So I think, yeah, L is known, right? L is known, right? L is 32.7, isn't it? Somewhere here we got the value here. For C note, L should be 32.7. For C note, L, the length should be 32.7, right? This is 32 point. This is the C note, right? Longest length produces the note C, right? So L, for 32 centimeters, actually it should produce 260, but it produces 255. That's the problem, right? So for this length, it should produce 260, but it actually produces 255. Therefore, we reduce the length a bit from 32.7. Okay, so length here is 32.7. So 255 over 260, 32.7 over 32.7 minus x. If you simplify, we're going to get x to something around 0.628 centimeters. So do not get panicked when you get this kind of ugly answers. Actually, these kind of answers are also possible in past papers, right? Like so you don't have to panic. Okay, so I got a very ugly answer. Like you're not going to always get some whole numbers as answers, right? So now things have changed very recently. You need to understand that, right? So like in the old papers, if you consider, of course, like most of the answers that you get are quite they are whole numbers most of the time. But now they have given some priority for the simplifications as well. So therefore, right, okay, that's the answer. So let us see if let's see the final fourth one. If the cork fell completely out of a pipe, what would happen to the fundamental frequency produced by the pipe? If the cork fell completely out of a pipe, what would happen to the fundamental frequency produced by the pipe? Justify your answer. Okay, so it's like this, right? It's like this. If you consider the fourth one, okay, there's the pipe, right? Now there's the cork as well. Cork. All right. Now if this fell, you are going to get what? You are going to get a open end tube. This is closed. One end closed. This is open end tube. Now what happens? In this case, of course, at the open end, definitely the condition is somehow you need to have a node, but in the open end, somehow at these 2 points you need to have antinodes. So therefore this is the waveform that is possible. This is the waveform that is possible, right? So what happens is, here this is lambda over 4. This is actually lambda over 4 plus lambda over 4, lambda over 2. So therefore lambda becomes double, right? Lambda becomes double. All right. So simply, what would happen to the fundamental frequency? If you see the fundamental frequency of this is 1 over V over 4L. But if you see the fundamental frequency of this, it's going to be V over 2L. V over 2L. Actually, you can write this, okay, this is F1, F2. Actually, you can write F2 as 2 times V over 4L, isn't it? Like if you cut to this, you're still going to get this. So F2 you can write as 2 times F1. So fundamental frequency has doubled, isn't it? It has doubled. The fundamental frequency of the open tube has doubled the fundamental frequency of the closed tube. So that would be the answer, guys. Right. So yeah, let us move on to the next one. Okay.